Today we're going to talk about momentum. Momentum is the quantity of mass in motion. To calculate momentum, you're going to multiply the mass in kilograms times the velocity in meters per second. Momentum is a vector, meaning that it has both a magnitude and a direction. We abbreviate momentum with the letter P. It's equal to mass times velocity, which is also a vector. So the direction of momentum will be the same as the direction of velocity. You can see that if we multiply kilograms times meters per second, we're going to come up with what's called a derived unit of kilogram meters per second. What are ways we can increase our momentum? Well, if momentum is affected by mass and velocity, essentially we have two options. We can increase our mass or we can increase our velocity. Let's practice calculating momentum. Again, momentum is equal to the product of mass times velocity. So I have a 3 kilogram ball moving at 5 meters per second. 3 times 5 is 15. Kilograms times meters per second is kilogram meters per second. Find the momentum of a 100-gram hockey puck moving at 40 meters per second. You need to convert to the appropriate units. So it's going to be 0.100 kilograms times 40 meters per second. And again, you plug it in. So 0.1 times 40 is going to be 4 kilogram meters per second. Number 3, find the momentum of a 0.15 gram bullet traveling east at 30 meters per second. So it's going to be 0.00015 because we need to make sure we're in kilograms times 330 meters per second. When I multiply that out, I get 0.0495 meters per second. And it is a vector, so we need to put the direction here. So east, the 4 kilogram meters per second in the second one would have been up, and the 15 kilogram meters per second would have been right. Find the momentum of a 100 kilogram truck stopped at a traffic light. Well, P is equal to M times V. So anything times 0 is going to be 0. Find the momentum of a 1,500 kilogram car moving at 10 meters per second. And that should be 15,000 kilogram meters per second. Question 7. Why would a football player try to run as fast as possible when making a tackle? Well, a tackle is a type of collision, which is really the main application of momentum. And why would I be trying to run as fast as possible? Well, momentum is equal to mass times velocity. So by running faster, I'm increasing my velocity, and therefore I'm increasing my momentum. Question 8. Why would a football player want to bulk up to increase their mass? Again, momentum is equal to mass times velocity. So if I want to increase my momentum, we've already looked at increasing the velocity. The second way I can increase it is increasing the mass. As mass increases, momentum increases. So that's why football players would want to bulk up or increase their mass as much as possible, because that's going to increase their momentum. In in this unit, so as I said, one of the main applications of momentum is going to be collisions. So momentum is always conserved. That means that the momentum before the collision is going to equal the momentum after the collision. The three types of momentum scenarios, or three types of collisions that we're going to talk about, are elastic. So think about an object running into another object. They're separate, and then afterward, they're also separate. In an inelastic collision, the objects are going to stick together. So imagine two objects that start separate. So something runs into another object. This is before. And then afterwards, they're going to remain stuck together. So elastic was start separate, end separate. Inelastic was start separate, end together. The last type of collision we're going to be looking at is recoil. Recoil occurs when the objects start together and end separate. So we have two objects that are starting together. Think about a cannon firing a cannonball, right? When the cannon fires the ball's going to go one way, the cannon's going to go another way. So those are the three types of collisions. Elastic, start separate, end separate. Inelastic, start separate, end together. And recoil, start together, end separate. We should also introduce the change in momentum. The change in momentum is given a special name called impulse. Impulse has units of kilogram meters per second, the same as momentum. However, we typically write them as Newton seconds. Newton seconds are equal to kilogram meters per second. It's just a different way of expressing the same unit. So, as you can see from the second law, we end up with the following expression. If we start with the second law, we substitute in the definition of acceleration, multiply both sides by time, and we end up with this. Force times time is equal to mass times change in velocity. Both of those expressions, force times time and mass times change in velocity, are equal to impulse, the change in momentum. Let's go ahead and take a look at the following examples of impulse. So in these three examples, I'm giving you a force and a time. Force and a time. So if I have 2 newtons times 60 seconds, that's going to be 120 newton seconds of impulse. 30 newtons for 4 seconds, so I've increased the force, decreased the time. You'll notice that we end up with the same total amount of impulse. A force of 120 newtons exerted for 1 second, so now we've really increased the force and really decreased the time, and yet the net result in terms of impulse is the same. All three examples give you a total of 120 newton seconds of impulse. This is a meaningful result in that you can realize a small force acting over a big time can cause the same change in momentum as a large force acting over a small time. And we'll be talking specifically about this in a few minutes. Let's try some additional practice problems. A force accelerates a 1,200 kilogram car from 10 meters per second to 18 meters per second in 15 seconds. Find the magnitude of force. So, I know that impulse is equal to mass times change in velocity, and it's also equal to force times time. So in this example, I'm solving for force, so I can go ahead and plug this in. Well, we'll just isolate for force. So it looks like force is equal to mass times change in velocity over time. So our mass is 1200. Our velocity, change in velocity is going to be 18 meters per second minus 10 meters per second for a change in velocity of 8 meters per second, all over 15 seconds. And if we multiply that out in our calculator, we get a total of 640 newtons for the force in that scenario. Let's try a second example. It takes a force of 1500 newtons, 20 seconds to stop a 1000 kilogram car for 20 seconds. Find the initial speed of the car. So again, we're going to start out with our expression for impulse, change in momentum, mass times change in velocity equals force times time. So in this case, we're actually looking for final velocity. So I'm going to divide both sides by m, and I get delta v is force times time over mass. We know change in velocity is going to be vf minus vi equals force times time over mass. Now in this example, we know that our final velocity is going to be 0. So in this case, we're really just solving for vi. There'll be a negative sign because the force is going to be in the opposite direction of velocity to show they're in opposite directions. So we know we have a force of 1500 newtons. It takes that force 20 seconds to stop this car, which has a mass of 1000 kilograms. So we go ahead and type that in our calculator. And when we do, we get that the initial velocity of the car was 30 meters per second. So now that you've understand the basics of the equation, we're going to get back to the fact that impulse, which is the product of force times time that I showed you up here, is that a small force acting over a long time accomplishes the same thing as a large force acting over a short time. One of the most obvious applications of this is going to be in automotive safety. You'll notice that your car is equipped with many things that seek to slow you down over a longer period of time in the event of an accident. Specifically, seat belts are meant to exert a force on you over a longer period of time. Airbags, instead of hitting the dashboard, it exerts a force on you over a longer period of time. Crumple zones, which are parts of the car which are designed to collapse in the event of a collision. And that's so the force that's slowing the car down and therefore you down is exerted over a greater time, so it can be a lesser force. And the reason you want a smaller force is so there's less acceleration, because that's where you're going to get injured when there's a really dramatic acceleration. You'll notice that if you touch the dashboards, they're also relatively soft. They're not hard plastic or wood anymore. They tend to be a soft touch plastic, which again will exert a force on you over a greater time than a harder material. We have a couple of kind of classic demonstrations for impulse. One would be if two students were to throw a water balloon back and forth, what would happen is when you were catching it, if you didn't want the water balloon to break, you would cradle it, meaning as you were catching the water balloon, you would move it back with you to slow it down. Whereas if you threw it against something that did not move back with the balloon, say throwing it against the wall, the water balloon would break. Another example would be an egg. If we were to throw an egg against the wall in this room, the egg would break. But if we were to throw it against a mattress or held up a sheet that would catch it, what that would do is exert a force over a smaller force over a greater period of time to cause the egg to slow down from its initial speed. So I'd mentioned automotive safety as one application of impulse. There's an organization called IIHS, the Insurance Institute for Highway Safety, which tests cars to determine their crash worthiness. In this video, you're going to be taking a look at two different automobiles. One, they're approximately the same year. One's a 2015, the other's a 2016. The difference is one is built to the specs in Mexico, and the second one I believe you're going to see is going to be built to the specs in the United States. Now, specifically what you're going to be thinking about here is impulse. What things in which vehicle allow us to have a smaller force over a greater time? Because ultimately, that's what's going to make the automobile safer. So they crashed into each other. You'll notice that the red car incurred some damage in the safety cage, which is where the occupants are. So one of the things you're probably noticing is that the silver car collapsed up into the point where it reached the cabin. Okay, we call this area a safety cage because it's designed of stronger steel to keep the people inside the car safe. Everything in front of that safety cage, right from the front of the car, essentially the length of the hood, is designed to collapse in the event of the crash. So again, what's that doing? It's exerting a smaller force over a larger time to slow you down from whatever your initial speed was. Now I'm going to take a look at the inside. So right away you're going to see this car did not have airbags, okay, which would have made it safer. This is the Mexico spec car. And the safety cage was not rigid. It collapsed on the occupant. This is the USA spec car. You'll notice there was an airbag and a side impact airbag, all of which served to increase the time over which the dummy was slowed down, minimizing his acceleration, and ultimately making the crash more safe. I would encourage you to take a minute to look up your own car, or perhaps a car that you're interested in, so you can see how it does in the third-party crash test results. Because automotive safety is very important to you and anyone that's riding with you. After that, we'll take a look at some more practice problems on calculating impulse. So remember, impulse, which is the change in momentum, is equal to force times time, or mass times change in velocity. So in question 1, Pat hits a 0.115 kilogram hockey puck with a force of 30 newtons over a period of 0.16 seconds. So you're going to be asking yourself, do I have force and time, or do I have mass and change in velocity? And in this case, you have force and time. So it's simply going to be a matter of plugging it in. We have 30 newtons times 0.16 seconds. If we multiply those out in our calculator, 30 times 0.16, we get 4.8 Newton seconds or kilogram meters per second. Remember, those units are identical. Now, we know that impulse is also equal to mass times change in velocity. So, it's equal to mass times the quantity Vf minus Vi. tells me the initial velocity was at rest, so my initial velocity here is going to be 0. So then when I plug it in, I know that 4.8 Newton seconds is going to be equal to 0.115 kilograms, which was the mass, times the final velocity. So if I divide both sides by 0.115, I'm going to get a final velocity of 41.7 meters per second. So why don't you take a few minutes and go ahead and solve the problems on this page so that you feel comfortable calculating impulse and finding speed, force, time, various practice problems. You have to remember that momentum and velocity are vectors. Let's take a look at problem 6 together. So Kenny Maddox and Norm Alfors are kicking a 0.25 kilogram soccer ball back and forth. When the ball gets to Kenny, it's traveling at 6 meters per second to the right. So let's just sketch this out. We're going at 6 meters per second. Kenny's going to kick that ball for a time of 0.02 seconds, and now it's traveling 14 meters per second left. So a common mistake would be to think that the change in velocity, delta v, is 8 meters per second. It's not, because when it's going left, the velocity, if we express it using signs, would be negative 14 meters per second. And so the delta v, the change in velocity, would be negative 14 minus 6, or a change of negative 20 meters per second. So this is going to matter because when you plug it into the impulse equation, force times time or mass times change in velocity, we're isolating for force here. So force is equal to mass times change in velocity all over time. So your mass was 0.25. Your change in velocity was negative 20. And our time was 0.02 seconds. So if we plug that into our calculator, we're going to get a force with a magnitude of 250 newtons. So go ahead and finish the impulse practice problems on this page. And remember, our main application here that we've talked about so far is automotive safety. So if we think about this scenario, a driver in a car accident is slowed from 30 meters per second to rest. The driver is slowed. Remember, our goal is small force, big time. So for example, in the one car, there was seatbelt, there was airbags, there were things that were really going to slow us down. And what they did is they gave us a small force acting over a long time. And again, the smaller the force, because of the second law, if force gets smaller, acceleration gets smaller, and the automobile ultimately gets safer. If we don't have airbags, if we don't have seatbelts, and the individual is brought to rest by just the steering wheel, for example, that's going to be an example of a large force acting over a short time. And that is not good, because if there's a big force, there's a big acceleration, and so that could be very dangerous. At this time, you're going to go ahead and complete any pages or any problems on pages 1 through 5 that we have not done. That'll give you a chance to practice calculating impulse, time, force, mass, and change in velocity.